Hi, I'm John Lockwood of Algo-Logic Systems, and I'm going to talk about real-time analytics and scale-out machine learning with an FPGA key-value store. I'm going to talk about a framework that we have that integrates the key-value store with the Markov Decision Process for the application of self-driving cars. The outline of the talk is to start by describing the Algo-Logic FPGA key-value store, and I'll show how it allows direct access of data both from the CPU and from the network. We'll see how it associates values, which are data, with keys that are names without the overhead of SQL. And we'll see how it's implemented completely in field programmable gate array logic. Next, we'll see how that scales out over Ethernet and PCI Express for wide-scale deployment in data centers and provides ultra-low latency at low cost. And lastly, we'll look at the application of accelerated machine learning for self-driving cars, and we'll see how machine learning, a Markov model, was used to enable cars to learn how to drive on a highway in minutes. Also for inference to ensure that cars drive using real-time data with deterministic latency. So first, what is the key-value store? So associates values with names, and these keys can be names, numbers, IDs, vertices. Data can be addresses, locations, graph edges. And key-value stores are an integral part of networking applications in the data center. They're used for tracking sensors, locations, movement, social, the status, updates. They're used in games. These for media, for video and security, and audio and music, and communication, the status of the network, handoff, messages, and databases to keep track of users, payments, travel, authentication, and security to keep track of warrants. So key-value store is a broad application, and we'll be looking at one of the applications in this. Algo-Logic's FPGA key-value store scales for the data center. First, it scales up to provide the best latency, throughput, and power. And it scales out to provide additional capacity, throughput, and redundancy. It's fully implemented in FPGA logic. It shares data over Ethernet. It supports the fastest in-memory storage for cloud services. Integrates into parallel file systems, and has a fully open software API. So it's easy to create, read, update, and delete key-value pairs. So servers accelerated with FPGA Gateware can be standard servers, such as an Intel CPU with a card plugged into it, or integrated into the socket, like the MCP. What Algo-Logic provides is what we call gateware-defined networking, which are applications like the key-value store that run in the FPGA logic. And it's that logic that provides applications with optimal latency, power, and throughput. The architecture of a key-value store in the network usually starts with input devices, such as IoT devices, live data that's streaming in from the top left of the diagram, and going into the cloud. And in the cloud, we have database servers that can store data in SRAM, DRAM, NVMe, Optane, and run database applications like Mongo, Redis, InfluxDB, and the Algo-Logic key-value store. We also have compute servers for doing machine learning that can be machines like a Xeon Skylake, a Xeon Phi, Nirvana, or even FPGAs. On the top right of the diagram, we have the actions that are being taken, the real-time actions. So the real-time actions are a function of the real-time input data, as well as what we've learned from our machine learning application, which are usually stored as weights or states in the key-value store. So we can make real-time decisions based on what we've learned in the past and the real-time data that's streaming in from the internet. So machine learning applications benefit from a key-value store by sharing data over the infrastructure. So the Markov decision process chooses actions given a current state. And starting from the bottom left, the key-value store stores the state of the system, and it chooses the transitions to next states based on the action that we take. And so based on the action from a current state, that yields our policy. And so by applying those actions and recording the outcomes from those actions, we can look at what rewards we get, such as having an accident or not having an accident. And we can update the Markov model so that when you take future actions, we can maximize the expected reward. So to model the system state is that we need to discretize the state of the system. And so the state of the system is a function of the velocity of the car, are the distance to the car in front of us, the relative velocity of the car in front of us, and indicators to see if there's cars to our left, right, front, and back. In the decision process is given the current state, how should the car act? And so the available actions in this case are to coast, or to press the gas, or to brake, or to merge left, or to merge right. So over time, the system transitions from one state to another, and it spends a different amount of time in each of these states. We can approximate the probability of transitioning to a new state, given the current state in action, by keeping track of distributions for all possible actions and states. We can count the state transitions from the beginning of time, and we can estimate the probability of the state transitions that's proportional to the time that we spent in each of those states during the simulation. We have reward values, and so we can have an immediate reward value, which is a positive or negative value for being in a certain state, as well as a subsequent expected reward, which is a long-term reward that we get for arriving at a state, which is the sum of the discount rate times the reward of the future states. So we want to choose an action that maximizes the expected future reward. We do that by keeping track of the immediate reward if we go into a new state, as well as estimating the value of subsequent rewards if we go into that new state, which is discounted by how far in the future we want to look. And so the action that we take is to maximize the best future expected reward for each of the probability of transitioning to a new state from a current state in action times the reward we get in that new state and the total value of the subsequent rewards from that new state. We can estimate the future reward from a state by calculating the action from that state as the reward and the future reward times the sum of the probabilities from a state in action we take to a future state, and then summing the probability of taking that action from the state times the reward that we'll get in the future state. So now, let's talk about the application of accelerated learning for self-driving cars. And so in this framework, we can have multiple instances of the self-driving cars thrown on a highway and interact with each other. And as these cars are driving, the idea is to maximize the time without having an accident. And so in the main window, we run the cars at human scale speeds on the highway. But in the background, we could run parallel training processes that run as fast as the simulator can go on the slave machines. So we can run parallel simulations on parallel machines at faster than real time and do hundreds to thousands to millions of simulations on a cluster of machines. And we use the key value store to search for data and to share data. And as key value pairs are modified over the network, the learning process improves. So now let's talk about how we simulate and learn. So first, we attempt to drive the car using the best policy. From a given state, we record all the state transitions in the key value store. And we look at how much time we spend before an incident occurs. That incident can be a crash or speeding or stalling. And we update that time in the database. And then we repeat. And so the learning process is to look at the time that we spend in each state and compute the policy, and then update the policy and repeat. And so we're continually refining the policy that we use to drive. So now, let's look at the framework running in real time. And so in this, we throw down 25 instances of the self-driving car. And in this, we're starting from the perspective of one of the instances, the blue car, as it's looking down the road. Each car is initialized at a different location on the highway and has a different initial cruise control speed that it's trying to maintain. And so then the cars need to speed up or brake or shift lanes in order to try to maintain their cruise control speed without hitting another car. And so as the cars drive, if there's an accident, the simulation resets and we learn from that accident about what led to a negative outcome and refine the model so that we're driving better. And so as this car is driving now, it has congestion ahead, and so it's slowing down, but if it slows down too much, it gets rear-ended from the back. So now, let's look at the system components. First, we have a Markov model server, which is continually updating the probability transitions from a state and action to the next state, the policy that we take from a state, and the reward of the states. We have multiple parallel compute servers that are simulating driving using the current policy and recording all the state transitions. We also have the display client, which is showing the live simulation on the screen. And then underneath all of this, we have the key value store, which is keeping track of the state tables, the action tables, and the transition counters. And it's sharing that data between the Markov model server, the parallel compute servers, and the display client in real time. So now let's look at the physical setup of the system. We have a 10 gigabit Ethernet switch at the top of the rack. We have a compute server, which has both the FPGA card with the key value store in one slot and the Xeon processor on the motherboard for doing compute. And then we have a display server on the bottom, which has the video output, which is driving the screen and pulling data in from the key value store in order to plot the current state of the system. And so the compute server has the FPGA card in a PCI Express slot. It has the Xeon CPU on the motherboard. It all fits into a standard 1U rack chassis. So we can scale out the system into a rack by having multiple instances of the scale-out compute server with the Xeon and FPGA, a display server, and an Ethernet switch. And then from the live dashboard, as we run from the display client, we can see the time between accidents is getting longer and longer, and that the key value store is handling dispersed of traffic as we have one or more parallel servers that are running to do these simulations. So now let's look at the parallel framework running again. After a few minutes of simulation, we can see that the cars are driving a little bit less erratically. We can see that the cars are accelerating and braking more smoothly and avoiding lane changes that are causing accidents. And so over time, the system gets better and better at driving. So within a few minutes, we're able to simulate the system tens of thousands of times. We're searching and modifying the key value store millions of times, and we're continually improving the time between accidents. So the key value store stays busy as the Markov model reads simulation results and writes policies. The parallel processes for the simulators are reading the policy and writing out simulation results. And then lastly, the display server is doing real-time analytics to drive the car. So real benefit of the key value store in the FPGA is the latency. And so this plot shows the latency distribution of 3 different implementations of a key value store. And so first in red is the software implementation of the key value store written as a traditional socket application running on an operating system. And so we see that the read latency over the network is about 42 microseconds. Now if we bypass the operating system and have a user space process directly process the key value store, we can get down into single-digit microsecond latency. But the FPGA key value store shown in blue gives us another order of magnitude improvement in the latency. And so at the FPGA key value store, we have an average latency of under half a microsecond and almost no jitter. So the key value store in the data center has several advantages. It lowers the latency by a factor of 88 over Linux networking sockets and a factor of 14 over kernel bypass. It also increases throughput, between 3 to 13 times improvement in throughput, which lowers the cost of the purchase of the system because the cores can be used for the more valuable function, such as simulating and running the Markov model. It also reduces the overall power of the system. So the key value store has a 13 to 20x reduction in power, and so that reduces the operating expenditure of running these parallel simulations. So there are many other applications for the Markov decision process and real-time analytics. In the transportation industry, airlines, taxis, and trucking fleets can use this framework to determine optimal coverage zones, schedules, and asset allocation. For retail banking, financial loan and mortgage firms can use this framework to classify good, risky, bad, and paid-up loans to minimize the loan risk portfolio. For financial services or fintech, there's multiple applications. Automated trading engines can detect patterns to maximize profitability. They can detect and react to news that shocks the market. And exchanges can classify and adjust commission rates for online trading volume. On the power generation side is that utilities can use this framework to adjust how different types of power generation are used and supplemented. For industrial materials and manufacturing, we can look at how to make optimal purchases of raw materials as the prices fluctuate. And for durable goods, such as the automobile industry, we can look at trends of the frequency of purchases, repairs, and replacement. For web services, such as search, is that you can look at how different word choices can be made while entering. And for weather forecasting and agriculture, we can look at how to make recommendations for optimal crops, types, acreage size, watering requirements, and harvesting. Even more applications for the Markov decision process and real-time analytics with the key value store would be to help build connected cities where we want public safety and real-time response to emergencies. For auto and trucks, the fleet management, for self-driving cars, and providing feedback for navigation systems. For the banking and securities industry, providing analytics and fraud detection for risk management. For the pharmaceutical and genomics, is that diagnosing and keeping track of health records and trends. For superstores, managing logistics, delivering inventory management. For machine trading, recognizing patterns. In the data center, managing cache control and memory management. For automated factories, providing maintenance and assembly line automation. In drones, surveillance, and aerial monitoring and analysis. And for power grids, optimizing power generation and load balancing. So many applications for this framework that can be scaled with the key value store to handle large problems. And so for more information, visit Algo-Logic Systems on the web at algo-logic.com, on Twitter at algo_logic_inc, or by email to info@algo-logic.com. Or visit us in Silicon Valley at our new address in San Jose, California. Thanks.